Hi, I'm Tasos, and here is Aaron. Later is going to present another part of the presentation. So, speed. Speed. Why does it matter? Someone might say it's quite, self-evident, but we care about speed in Sui a lot because we care about the dApps. We care about being, fast, responsive. And why is that? Because we care about our end users. We care about the end experience. And we want to do that. We want to deliver like fast speed on our blockchain and do that in a reliable and consistent manner. That is also very, very important to us. So what are we going to talk about today? We're going to talk about how we think on performance. We're going to touch a little bit on the transaction life cycles. We can set a little bit the grounds. Then Aaron is going to present about the new consensus engine that we are currently integrating, the Mysteti or Consensus 2.0, as we call it. And then in the end, we're going to touch on the end-to-end dApp latency. So, quick overview. How do we think about speed? So, the most important metric is like the end-to-end latency of the user, is the latency that the user perceives, But from engineer perspective, we also care about, and something that you probably have heard is like the term finality. And in Sui, we also, break down finality like in two subcategories. It's like the transaction finality and the settlement finality, and both matter here. So the transaction finality is like, by the moment I submit my transaction, getting back a promise that my transaction will get eventually executed. Does not execute it yet, I get a promise. So the settlement finality is actually having my transaction get executed, be on chain, and everyone be able to see the result. We don't care about the result, success or not failure. We care about the fact that it gets executed. And those two metrics have to correlate a great deal with the end-to-end latency, which we try to push down. Now, we can't have everything in life, and that is when we talk about throughput and latency and fast commit. So, ideal world, we want to be as fast as possible and have the highest possible throughput. So we want to be on the top right corner, and this is what we try to do with Mysticeti. Today, we have very good latency, but we are not that satisfied. We want to push the envelope. We have the high throughput, and we can see a comparison with the some like example other protocols today. So let's talk a little bit the transaction lifecycle. So we have two transaction types, as many of you already know. So we have the owned object transactions, which are transactions that have objects that can be mutated by one writer. And those transactions that don't need to go through consensus. They need to go through our fast path, which is today the fastest offering we have. Some examples, coin balances and transfers, some NFT minting, some in-game logic asset management creation. And then we have the shared object transactions. And in order to execute those transactions, first we need to sequence them. So they have to go through a little bit more slower path here. An example is a public accessible calendar, an auction, marketplaces, stuff like that. Now, let's assume that we have, I'm going to show you a little bit of what is the journey, the transaction journey here. So let's assume that we have our user, this lovely Cappy here, and we have our network of validators. So the first step is the basic protocol is a two-phase protocol here. So the first step is like for you, the user, to put together a transaction, sign it, and everything. Broadcast it to the validators. So at that point, the validators, they just do validation, they don't do execution, and they make the promise that they will execute this transaction at some point in the future once we instruct them to do so. Once the user gets back a majority of responses, a quorum of responses, then the user creates what we call a transaction certificate. And now this is the promise on my hand that, okay, I can now go and instruct the validators to execute this transaction. So again, the second phase begins, and we're sending this transaction back to the validators. We broadcast it, And once we get back the quorum of responses after the execution, now we have the effects certificate. So now my transaction has been executed. The results are in chain and are irreversible. How fast is that? 2 RTTs, only 2 RTTs. Shared objects. The story is quite the same up to the first phase, but we have a difference in the second phase. So here, because we have to use consensus before we execute, first, our validators need to send the transaction certificate to our consensus. Today is Narwhal and Bullshark. This is our lovely Bullshark. We love it. It's very good, but we want to improve it. And after it gets sequenced the transaction, now the validators can go and execute it. So, similar story, once the user gets back a quorum of responses and has the effect certificate, now we know that the transaction is on chain. So, how fast is consensus here? It is a bit hard sometimes to explain things on RTTs, but the base case that we can have here is roughly 4.5 RTTs. And this is our opportunity for improvement when it comes to consensus. So, our whole path here is like 6.5 RTTs. We're going to explain about the overall end-to-end story, but for now, this is what you probably need to keep here. So, as I said, the opportunity is to bring down the consensus latency. How we will manage to do that? Now, Arun, you're here, sorry, is going to explain how we're going to do that with Mysticeti.
Awesome. Thanks, Tasos. So I'm really excited to talk about consensus today. But fair warning, if this is your first time hearing about how consensus works, it can be a pretty complicated topic to digest. So we're not fully expecting to understand it in the next 10 minutes. But if you can kind of stick with us, there's some nice diagrams. And what we're hoping is you can kind of get the high-level overview of how it works and some of the intuition behind it. So first, let's look at what exists out there. What are the protocols that exist out there? So you have one category of protocols called the linear-based protocols, and this is like PBFT, Tendermint, and Hot Stuff. And so these protocols are leader-based protocols. So what you have is here in this image here is leader C is in charge of gathering transactions. It'll create a block. It'll then get votes or validations for that block, and then include that block on chain. And so this process is repeated, and this is how you end up with your blockchain. So these protocols are often bottlenecked by leader bandwidth because, as you can see here, the leader has unproportionally a larger amount of work to do than the rest of the network. And so you also have this property where now the network has to be strongly connected with the leader. So if the leader crashes, what ends up happening is now the rest of the network has to elect and agree on a new leader. And during this time, it can be pretty complex, so it's time consuming. The network is unable to process new transactions, so throughput stalls. But what this does offer is it does offer low latency. So what to take away from this? Linear-based protocols, low throughput, low latency. Then we have the DAG-based protocol. So a DAG is a directed acyclic graph. And so what we're building here is a leaderless DAG. And so what we can see here is that all of the nodes in the network are able to propose blocks. So what does this allow? It allows us to fully utilize our network bandwidth, which is great. Right now, all the network is sharing their resources evenly. And so when you think about DAG-based protocols, what we do is we separate transaction dissemination, so building of the DAG, and then the actual commit logic, which is reading the DAG. So we have Narwhal, which does the transaction dissemination, and then we have the reading or the commit logic, which is Tusk and Bullshark. And so today, we'll go over what we use today, but we use Narwhal and Bullshark. So what DAG-based protocols offer as well is because it's leaderless to construct the DAG, even though the commit logic is leader-based, if the commit logic misses a leader, it fails to commit. But the actual building of the DAG can continue on even if the leader is missing. And so this is how we maintain a high throughput, because eventually a leader will come in that we can commit, and the sub-DAGs of the missing blocks, those blocks will eventually get committed. But what this does have the drawback of is higher latency. And so like we talked about before, the goal is we want high throughput and low latency. So what do we have today? In Sui today is Consensus 1.0 or Narwhal and Bullshark. So let's just go over how this works. So the Narwhal piece of building the DAG, we first have to do 3 steps within a round. First is we propose a block, then we vote on that block. So the network will then vote, which is a network message. Once enough votes are gathered, a certificate or a certified block will be created, and then that will be broadcasted. So as you can see here, we have 3 network messages that have to be sent within the round. So that's 1.5 RTTs per round. And then the bull shark or reading of the DAG on top of that to be able to commit or sequence the blocks, that requires that every even round will elect a leader, and then we'll use the odd rounds to vote for that leader. So all a vote is if there's enough links to that block from the previous round, we can say we can commit it. So in the happy path, we need at least 2 rounds to be able to commit a block. And that's about 3 RTTs. So what are we trying to do tomorrow? Not literally tomorrow, but in the future. We're building Consensus 2.0, which is Mysteti. And so what the intuition here is, what if we could, instead of having these separate network messages that go in to certify the blocks and create this certified DAG, what if we could operate on an uncertified DAG? And we can just optimistically send uncertified blocks to the network. And so we're just gonna be broadcasting blocks. If we do that, every round can then end up being half an RTT. So let's go into how that uncertified DAG gets built. So similar to other DAG-based blockchains or DAG-based protocols, we have a block that contains a round number, an author, a list of transactions, signatures, and then links to your parents. So before I keep going, you're gonna often hear 2f+1 quorum. So in BFD systems or Byzantine fault tolerance systems, you have up to f faults that you can handle. And so if we have 4 nodes in most of our examples here for ease of explanation, a quorum is just 2/3 majority or 3 nodes. So you hear me say that, that's all that means. Okay, so we have some rules while we're building the DAG. So the first rule is when you propose a block, you have to link to 2f+1 of your parents. And so that's the first rule. So you can see in the diagram, the yellow block has 3 links to its parents. Easy enough. The second rule is, even though the DAG construction is leaderless, when we read the DAG or try to do commits, we need to have connections to our leaders. So best effort, rule number 2 is we want to wait to see if we can connect to our leader. And so you can see here, we have a link to the leader L1 there. Awesome. And so then, just like other DAG-based protocols, when we're building, all nodes do this in parallel, and this is all we have to do. And so when building an uncertified DAG, Mysteti, the one operation it has is just broadcasting blocks. And this is in contrast to Narwhal, which has the vote, and then the certify phases as well. So what does this look like? So if we start building our DAG every round, we're broadcasting blocks. We have a DAG like we've seen before, but this is an uncertified DAG. So the key ingredient to Mysticeti is that instead of sending within a round a separate network message that will propose, vote, and certify, what if while we're building the DAG, we can piggyback on these network messages that are broadcasting blocks, and then we'll vote and certify for the blocks at the same time? So that's what we do. So we have these logical waves of 3 rounds, the same 0.5 RTT each. And while we're broadcasting blocks, at the same time, what we're doing is we're saying we can then vote and certify for these blocks. And that is something that we'll do when we're interpreting the DAG. So we'll see here that concludes, we'll have multiple waves. Every 3 rounds, we'll have a leader elected. We'll propose, vote, certify. And I'll explain this more as we go into interpreting the DAG. So this is a part that I mentioned earlier. So you have the DAG construction, and then you actually have to read the DAG and make some decisions. So I'm going to try and break it down for you in a way that might be easy to understand, hopefully. And all you're really looking for are certain patterns as you start to look at the DAG. And so if you look here in round 2, we have these green blocks. These green blocks are what we call votes. And so the second round of a wave is a voting round. And as long as a block links to a leader, we consider that a vote. So then the negative is true. If a block doesn't link to a leader, we call it a non-vote. That's one of the 2 patterns you have to recognize there. The other pattern is called a certificate. So a certificate in round 3 of the wave just links to 2f+1 votes. So if you can remember those 3 patterns, then we can follow the commit rules of Mysteti. So the first rule of Mysteti is called the direct decision rule. And so these rules allow us to make commit decisions. So the first is, if we see 2f+1 non-votes, so this is in the voting round, the 3 red blocks, if we see 2f+1 non-votes, we know we have to skip that leader. Great, we made a commit decision. But if we see that we have 2f+1 certificates, we can identify that pattern, then we can say we can commit that leader. If we can do neither of these rules, then we mark that as undecided. And so the important part about Mysticeti is that because it's an uncertified DAG, you have to have this extra step of marking blocks as undecided. Because every validator has a different view of the DAG, we don't know at what point what information they have received yet. So there's future commits that might be able to happen, but we have to stop if we don't have enough information. So then what happens? If we have an undecided block, we do eventually need to make a commit decision. So we have an indirect decision rule, which just means if there's a leader that gets committed in a future wave, we can use that to try and commit undecided blocks. So here we have L2, which is part of wave 2 of the next wave. That got committed. So now what we're looking for is just another pattern. Is there a path, a DAG path from L2 to L1 that goes through a certificate? And that's really it. So as long as you can find a path from L2 to L1 that has a certificate in it, then you're good to commit it. If not, you mark it as skipped. And those are the 2 rules. And this is how we come to commit decisions. But Mysticeti takes it a step further, and this is called the universal commit rule. So what this means is that anywhere in the DAG, if all validators agree to make a commit decision from that block, we can actually achieve consensus on a commit decision. And so that's why it's called the universal commit rule. So what we've seen is we make commit decisions from a leader, but what if, so in the previous examples, you've seen every wave we elect 1 leader. But what if instead of waiting 3 rounds to elect a leader or at the end of a wave, what if we started a wave from round 2 as well? And then from round 3 as well? This is what we call pipelining. So instead of waiting now, we have the proposed vote certified because we have the 3 rounds for wave 1, the yellow wave. We would have to originally wait for the next wave that starts at round 4 to complete to elect our next leader and then commit that. But what we can do now is that we have the blue wave that's completed at the same time, and now we have the opportunity to interpret the DAG and try and commit L2A. And so this is the beauty of the universal commit rule, is that now we can elect multiple leaders. So, like I said, it can be from any block, right? So if we take this a step further, we can actually elect leaders, multiple leaders per round, and then we can rank them and then try and run the commit rule on those leaders. So there's diminishing returns for having every single block be a leader. So in practice, we'll most likely have 1 to 2 leaders per round. So you've done the hard part. You made the commit decisions. You figured out what you're going to commit. Now you have to actually order the leaders. And actually, this is the easiest part. So you go through and you see your leaders that you've made commit decisions for. So L1A, L2A, L3A, L4A. And when you get to L5A, you've actually reached an undecided leader. And so even though there's leaders after it we have commit decisions for, because we are unsure about what the commit decision is for this leader, we do have to stop. And eventually we'll get more information and we'll make a commit decision. So then what you do is we have a sequence of leaders. We'll skip or drop, we'll drop the skip leader, and then now we have the 3 leaders that we just need to collect their subdags using any deterministic graph traversal like depth first search, and then we'll linearize that, and that is the output of consensus. So, okay, cool. So you made it through. So what does this really mean, right? So what does this mean in terms of latency and for builders that are building on top of this? So for Consensus 1.0, which is Narwhal and Bullshark, we estimate, the happy path is 2 RTTs due to misleaders or not enough support. We estimate about 4.5 RTTs on average for latency. And so the drop in theory then for Consensus 2.0 under the same conditions is about 2 RTTs. So just to recap how we did this, we moved from a certified DAG to an uncertified DAG. We went from only committing leaders on even rounds to now we enable pipelining, so now we can elect a leader every round. And then we've taken it a step further, so instead of a single leader per round, we can have multi-leader proposals. And so this is the alpha. This is numbers that you guys are seeing for the first time. So we have Mysticeti running in private testnet right now. Private testnet is built just to be kind of a replica of mainnet. So similar stake and geo distribution, similar load, and similar number of validators. And so what you can see here is that the actual average latency has dropped about 78% in the average case. So this is the P50 latency, and then the P95, we've dropped about 73%. So we're really excited for you guys to be able to use our new consensus engine, and Tasos will come up to talk more about the larger picture and the rollout.
Amazing. Thanks so much, Arun. That is amazing. Okay, cool. So what we talked about, so far, it is part of the story. So there is a little bit more into it. So we talked about, all the parts that have to deal with mainly, the finality, what is going on in the network once you submit your transaction, the consensus, the new consensus, and how fast we manage, to get to the execution. But there is a little bit more into it. And again, we care about the DApp responsiveness here. So we have some paths that they still affect latency. They are sources of latency. And these are like pre-submission and the post-submission RPCs. And more specifically, we can see that many applications, before they are able to initiate a new transaction, first they need to get the latest versions of the objects and then initiate their transaction. So from a system perspective, what does that mean? It means an additional RTT from the user app to the full node to the RPC and get back the information that needs. So that's an additional source of latency here. And there is also post-submission stuff that are happening. So after the transaction has been executed, sequence executed and so on, like the checkpoint certification, the state synchronization, the indexing. Again, this is the part like after all the things that we have talked so far that take place, which also involve like additional time, additional RTTs here. And we also working to improve that story by making improvements on our SDKs. So one of the improvements that the team is working on is on memoizing the transaction effects. So that will eliminate the need, or at least in the common case, to use the pre-submission RPCs to get, for instance, the first gathering of the latest object versions, and also the RPCs to propagate the new object content back to the clients, which is after execution. So that will allow the SDKs to use the data for calculating auxiliary info here. So again, for the common cases, probably not need to go back to the RPC nodes and make additional requests. So making the apps more responsive and faster. So summing everything up, speed, it matters for us. It matters the end user experience. So thinking, top to bottom, we want to allow our users to have the best possible experience. How do we do that? We try to improve our protocols. How do we do that? We think about the RTTs, how we can minimize those. Arun showed you like a great deal of the work in Mysteti here. So we managed today for the shared object transactions, to have like a finality, a settlement finality, like around 700 milliseconds, which is, amazing. This is like in practice. So what is our roadmap for those improvements? We're, for the consensus 2.2 rollout, we are going to hit testnet probably end of April and May. Those are target dates. On mainnet, we are targeting around June and July. And for the SDK improvements, similarly, we are targeting for roll those out June and July. So thanks everyone in Bench from myself and Arun. And if you got any questions, please come, and find us. We're going to be here today, tomorrow, and similarly, maybe on Friday.